So in the last class we are discussing about the actually I am recording that class in my laptop, and I will, if it doesn't make any problem, so I will give that to the upload that in the file. Okay, so today we are going to discuss about the very simplest type of rectifier circuit that you have already studied, that is your half bridge rectifier with a resistive load. And as you can see, when your anode voltage, that we said before, when your anode voltage is greater than your cathode voltage, then what will happen? The diode will start operating, right? Or it will be just like a short circuit, right? So we are considering this diode to be a ideal one. So whenever you have a positive voltage, we will assume that the diode, it will be short circuited, right? And as the diode is short circuited, all the input voltage, it will appear across the resistance, right? So that's why you will find that the output voltage from 0 to pi, it will be the same as your input voltage, right? But for the positive half, the voltage polarities was like this, right? But when you have a negative cycle, so what will happen here? So the polarities will be reversed, right? So then it will be negative and it will be positive terminal. So it will try to force the current through the opposite direction, right? So in that case, you will find that your cathode voltage will be higher as compared to the anode. So when this is happening, so what will happen? So the circuit, it will basically look like this. So that the diode will be turned off. So let me draw that again. So now, since diode is turned off, so all the input voltage that you have, it will appear across the diode, right? Because there is no current flowing in the circuit, so there will be no resistive drop here, right? Meaning your output voltage, which is nothing but multiplication of current with the resistance, it will become 0, right? And for this section, it will be 0, but the entire negative half cycle, it will appear across the diode, right? But in the first case, the diode became short circuit, so the voltage across the diode was 0, right? So the voltage across the diode was 0, but since the voltage across the diode was 0, so entire input voltage, it came across the output, right? So this should be the output waveform, and the last one, it should be the waveform for the diode voltage, right? So now if I want to get the average value of the output voltage, so what we can write? So my V naught average, it should be what? 1 over 2 pi, then we have voltage from 0 to pi, right? So it should be 0 to pi, then it should be Vm sine omega t d of omega t, because we are considering in making the integration with respect to not time, angle theta, right? And theta is nothing but omega t, right? So if we integrate sine omega t, then what you will get? Vm over 2 pi, it should be 0 to pi sine omega t multiplied by d omega t. So if you integrate that one, you will get Vm over 2 pi, integration should be minus cos omega t, right? And it should have a limit from 0 to pi, right? So you will get Vm over 2 pi, then it should be minus cos pi plus cos 0, right? So that gives you Vm over 2 pi 1 plus 1. So that gives you Vm over 2 pi multiplied by 2. So finally you get Vm over pi, right? So that should be your average value. So what should be the average current then? Your I naught, it should be V naught average over R. So that gives you Vm over pi multiplied by R. That should be your average current, right? Right? So now if I want to get the RMS value of the voltage, output voltage, then how we can write that? So my V naught RMS, it should be square root of 1 over 2 pi. It should have the same value 0 to pi, but this time it should be Vm sine omega t whole square and then d omega t, right? So you know how to do this integration, right? So I will not go in detail of that one. And similarly my I naught RMS, it should be V naught RMS over R, right? So based on this value, you can calculate all the parameters that we have discussed in the last class, like the power factor, the transformer utilization factor, and all the parameters that form factor, everything that we have discussed in the last class. Based on that, you can calculate all the parameters, right? So I will not go into that into detail because I don't want to spend much time on this. The next thing that I want to discuss today, and I will put my full class on this topic, this is the half wave rectifier with RL load. And why it is so significant? Because all the loads that we have in practice, they are basically RL load, right? Okay. So now, if we consider that this diode is turned on, then what will happen? If the diode is turned on, so the entire voltage, it will appear across the output, right? So we can write VRT plus VLT, that should be equals to my Vm sine omega t, right? So instead of VRT, what we can write? R multiplied by I of t. Yeah, it closed after 5 minutes. So then again we can write L di of t over dt, that should be equals to my Vm sine omega t. This is my equation, right? So now if I want to get solution for I of t, it's a simple differential equation, right? And you know how to get the response for this current, right? So my I of t, it will basically have two components. One is called natural component INT, and another component which is known as forced component, which will be, so basically if you have a differential equation, you have a natural component which is known as the complementary function. You have learned that, right, for the differential equation. And there is another part which is known as PI, right, particular integral, right? So this natural solution, it is basically your transient response, and the forced response, it is basically your steady state response. So how we can get the transient response or the complementary function? So if I put R I of t plus L into di t over dt, that becomes 0. So that gives you the, if you want to try to solve this function, then that portion, it will give you the complementary function, right? And if you divide it by r, so I of t plus L over r multiplied by dit over dt, that should be equals to 0. So finally we can write it as int, it should be my sum constant a e to the power minus t over tau, where tau is this factor which is known as time constant, right? L over r. You have learned this in your circuit class, right? Linear circuit as well as in mathematics, right? And the second part, which is the steady state response. So suppose you are putting a sinusoidal source to a RL load. So what will be the steady state response? Suppose you have a source Vs, it should be what? Vm over root 2, right? So what should be your I then? I then should be Vs over Zs, right? Right? So that should be the phasor, which is your steady state response, right? So what should be this steady state response then? Your I force t, it should be equals to Vm over Z, that should be your magnitude, right? And it should be sine omega t minus theta. What is my theta? Theta is what? Tan inverse omega L over r, right? And what is Z? Z is r square plus omega L whole square, right? So now if I combine them together, so what would be my I of t? So my I of t, it would be a e to the power minus t over tau plus Vm over Z sine omega t minus theta. That should be your equation number 6, right? So this should be my response for current, right? Any question? Any question? Okay. So now if I consider if we consider I of 0 is 0, so current is 0 at the initial. So what we can write then? I of 0, which is again 0, it can be equals to a multiplied by e to the power minus 0 over tau plus Vm Z sine 0 minus theta. So that gives you a plus Vm over Z sine minus theta. Sine minus theta is what? Minus sine theta, right? So we can write a minus Vm over Z sine theta, that should be equals to 0, or finally we can write a is nothing but Vm over Z multiplied by sine theta. Make sense? So now if I put this value in 6, so from 6 we can write, so from 6 we get my I of t, it should be equals to Vm over Z sine theta multiplied by e to the power minus t over tau plus Vm over Z sine omega t minus theta, right? So that is the current response with respect to time. But if we want to get the time response, current response with respect to omega t, so how we can modify this equation? So we can write then Vm over Z sine theta you have to replace every t by omega t. So it should be e to the power minus omega t divided by omega tau plus Vm over z sine omega t minus theta. So that should be your current equation of a RL circuit with respect to the angle, right? So now how this current will look like? So for that one I just copied some waveform from, so whatever we are discussing today, it is taken from your hard book chapter 3 and Ned Mohan's book chapter 5. So hard book chapter 3.
So how can we just replace T with omega? After the last line.
Yeah, just here we have omega t here, right? So here we just have t, right? So just
we have another T in the sine omega T minus theta.
yeah, but it is already omega t is present here, right?
But if we are
So omega t is what? Your theta, right?
my question is, if we are replacing all the T's with omega T,
No, we are not replacing that one. We are replacing, want to just put the value of omega t, right? And we want to get the response of the circuit based on the omega t. So here you can see from the previous section, this portion only had t, right? But not omega t. But here we had the omega t, right? Because when we are deriving that equation, we are deriving that equation with respect to what? Omega t, right? So the only thing we need to do here, we just multiply both numerator and denominator by omega.
Sir, this makes no difference with the form.
No difference. But what it gives me is that instead of t, because in the previous thing, if I want to draw the waveform with respect to omega t, we have to calculate each and every time what is my t, right? Rather than that, now I can directly put the value of omega t or the angle, right?
I understand now. I missed the omega with the tau, so that's why.
No.
There is another omega.
Yeah, so I just multiply both section by omega. So now what will happen here? So let me draw this, see that thing. So this waveform is basically from hard book, and this waveform at the bottom, it is from Nid Mohan's book. And I will explain this curve also with the MATLAB Simulink today to explain how these properties are changing with the value of L and R. Okay. So now what is happening here? As you can see, this current, it is actually having a sine term in it, right? Because here we have sine theta, you have sine theta, right? Meaning that the current will have a waveform that is pretty much close to the sine wave, right? So here this current, as you can see, this current waveform, it is very close to the sine waveform. Okay, but we have to consider this point. So let me consider this point here, Nid Mohan's book. So here this waveform, it is representing your VR, and this waveform, it is actually your Vs, which is your source voltage. So the difference between these two, what is my VL? VL is what? Vs minus VR, right? And the voltage across VR, it is in phase with the current, right? Because voltage across the resistor, it will be in phase with the current, right? So if the current has shape like this, so if this is my current I, so the voltage across the resistor, it will have the same wave shape, right? Without any phase delay, right? So now before this point, what is the difference between Vs and Vr? This is this area, right? Because this is my Vs waveform and this is my Vr waveform, right? So Vs minus Vr, that gives you this area, right? So this, for this area, Vs is higher, Vr is lower, meaning that your VL is positive, right? So as you can see, the area that is my VL, it will be positive here, right? But after this point, what will happen? The current keeps going, but it is not zero, right? So the voltage will be same but differ in magnitude with the current wave shape, right? So here what will happen here after this point A, so what will happen? Your VL is Vs minus Vr, right? But this case Vr is higher, right? And Vs is lower. So what will happen? The inductor voltage, it will be negative, right? So when the voltage across the inductor is positive, what the inductor will do? It will be charging, right? Right? And the current through the inductor, it will be increasing. But when the voltage across the inductor is what? Negative, then what will happen? The inductor will discharge, right? And current through the inductor, it will be reducing, right? So what will happen, since the current is not zero here, but it is still continuing, so what will happen? The inductor will still discharging, right? And the only way for the inductor to discharge is through this diode, right? Because with this circuit doesn't have any alternative way for the inductor to discharge its current, right? So what this inductor will do, it will force the diode to remain turned on although your input voltage is what? Process zero level. Because the current through the inductor is not zero. Make sense? So if the current through the inductor is not zero, what it will do? It will force the inductor to make the diode turned on until unless it discharges the current to get to 0 point, right? So until unless if the diode is turned on, what will happen to the output voltage? Output voltage will be same as the input voltage, right? So if the current is 0 here, so before that what will happen to the inductor voltage, output voltage? It will have a negative portion of the input voltage as well, but this portion is what? Very small portion, because the diode is conducting, right? And the inductor current is forcing the diode to remain turned on. Make sense? So now what will be the average value of this output voltage? So my V naught average here, it should be what? 1 over 2 pi, then 0 to, it should be beta. So it should be 0 to beta, then Vm sin omega t, and then d omega t. Should it be higher or lower than what we have got for the average values when the resistive load was connected? Lower. Why is lower? Because it has a negative area to it, right? Right? And why this we are having this negative area? Because the diode voltage, although it was negative and it was discharging, but the current was not zero, right? So it needs certain time for the inductor to get fully discharged, and by this time it will keep the diode turned on so that the input voltage comes across the output. Make sense? So now, as I said, the resistor voltage, it will be the same replica of the current, but it will have different magnitude than the current waveform, right? And what will be the diode waveform? And as you can see, the inductor will have a positive and negative portion, right? Because some part of the portion, when your input voltage is greater than the resistive voltage, the inductor voltage will be positive, but when the resistive voltage will be higher than the input voltage, the inductor voltage will be negative, right? And since the diode is operating up to this part, so up to this part, what will happen? The diode voltage will be 0, right? Because it acts like a short circuit switch. But when the current becomes 0, then what happens? That since there is a polarity, reverse polarities, the diode will be turned off, right? So the inter voltage, it will appear across the diode, right? So what I am saying here, suppose you have a circuit and this is my diode, and you have a resistive load and inductive load. So current is flowing through this, but after some points the current becomes 0. But at that point, what was the polarities across it? The polarity was, this is negative, this is positive, right? So the cathode of the diode, it will be with the negative polarities, right, as compared to the positive that we have here, right? So diode will be what? Turned off, right? And when the diode is turned off, what will happen? There is no current, meaning that there will be no drop across this element, right? So if there is no drop across this element, what will happen? The diode will have the same voltage as the input voltage, right? Any confusion? Because no current, so inter voltage here, it should be what? 0, right? So here, if the voltage is 0, output voltage, then you have an input voltage, so diode voltage would be what? The difference between input voltage and output voltage, right? So in that case, what is your input? Negative, right? So the diode voltage would be exact the same polarities at the input voltage, right? So that's why you have a negative portion of the waveform. But this thing is missing. Why this thing is missing? Because the diode was forced to conduct by the inductor current. Make sense? So let's see how, okay, so now here we are assuming that after a certain point or angle beta, the diode current or the inductor current will be 0 as well, right? Because initially we considered that the initial current would be 0, right? But we found that after a certain angle also the current would be 0. So if we consider that at omega t equals to beta, my I of t, it would be 0 again. So what we can write then? So my I of beta, it should be equals to 0, and if I put this value here, what should be my value? Vm over z sin theta multiplied by e to the power minus beta over omega tau plus Vm over z sin beta minus theta, that should be equals to 0, right? So from that one we can write my sin theta multiplied by e to the power beta over omega tau plus sin beta minus theta, that should be equals to 0, right? And from that one we can calculate my value beta, for which my current will become 0. And this beta is dependent on what? The circuit parameters, the time constant as well as the resistance and the inductance value. Make sense? So whatever we have discussed today, as of now, let's see how we can do that in MATLAB Simulink.
This is not something helpful, right? This is the drawback of the inductor.
Right. Because my output voltage is getting lower, right?
Yeah.
So how we can do the remedy for that, we will discuss that within 5 to 10 minutes. Okay. So now let's see how the circuit reacts or works if we have a certain types of load. So suppose this is my load. This is the same circuit. So we had a 100 volt peak to peak value, and we considered this to be 60 hertz, because for your Daniel Hart book they considered everything to have 60 hertz. And we have a diode, and we have a inductance and resistance. So my inductance value is 0.1 and my resistance value is 100 ohm. So I just made one example from the Daniel Hart book. Okay, and now I want to simulate that thing. So if my frequency is 50 hertz, what is my time period? 20 millisecond, right? So if it is 60 hertz, the time period will be much lesser than that, right? So if I want to make that circuit simulate for 0.6 is what? 3 cycle, right? Three cycle, or 0.06 should be 3 cycle. Now can you see? So this is basically my resistance voltage, and this is my inductor voltage. So as you can see, the inductor has a positive portion as well as the negative portion, right? Because during this part the resistor voltage is less than your source voltage, so the inductor voltage was positive, right? But after this portion the resistive voltage is higher as compared to the source voltage, so the inductor will have a negative portion, right? And the voltage across the resistor, it should be the replica of the current, right? Because VR is what? I multiplied by R. So if you divide VR by R, you will get the current waveform, right? So this is the thing. And if I want to see the inductor current, so suppose this is my inductor current. If I want to see the inductor current now, so let me see the now can you see this waveform, the inductor current, it resembles almost what we discussed in the curve, right? It resembles like this, right? But how about if we change the value of L and R? Then what impact does it have on the circuit? For example, if we reduce the resistance, then whether the time constant, it will increase or decrease? Time constant will increase, right? Because it is L over R. So if you reduce the value of R, time constant will definitely increase, right? So now currently you have a resistance value of 100. So if I change this value to be 1, so I reduce the resistance or the time, I increase the time constant by 100 times. Okay, so what will happen to my simulation? Now you see, since I reducing the current, sorry, resistance value, so the impedance value it will be reduced, right? If I reduce the value of, so okay, so this is my total equation, right? So what is my z? Z is r square plus omega l whole square, right? So if I reduce the resistance value, then definitely z will reduce, right? And if z is reduced, then what will happen to the current? This value will increase, right? Meaning that the current will have higher value if we reduce the impedance value, right? So now what will happen to the current? If you want to see the waveform here, you suddenly see that if you increase the time constant, the current is almost on for the entire full cycle, right? Right? And if it is almost on for the entire full circuit, then what will happen to the output? So now let me see the output. So if I want to see the output, can you see the output now? Now, as you can see, the output is almost having the positive portion similar to that you have in the negative portion. So the entire output, the average value, it would be very small or very high? High or low? Because this area will be cancelled by this area, right? So the average value will be very low. So the more you try to conduct the inductor current, or if you want to the diode D1 to turn on for the huge amount of time, then what will happen to the output? The output will get reduced, right? Right? So how can we do the remedy of that? How can we do the remedy of that? Suppose we have a constant load, so we don't, suppose you have a fan where you cannot change the value of L and R, but your output is getting lower, right? So how you can change that situation? Any suggestion? Any suggestion? So let us do one thing. So suppose if we want to have the same circuit but output, if I want to have the output similar to what we had for the resistive load, then what we can do, we can modify the circuit like this. So suppose we have a simple voltage source, this is my Vm sine omega t, we have a diode, that is my D1, and then we will have another diode, that is D2. This diode is known as freewheeling diode. And then we can have the resistive load or the inductive load, and this is my output V0, this is my VR, this is my VL. Okay, so what we are going to do here, so suppose we are applying the same input voltage here. So suppose this is my omega t, we are considering 4 equal space, so I can draw it like this. So suppose this is my 2 wave, this is my Vs, and this is my Vm sine omega t, that is my input. So now what will be my current? So from that equation we found that my current will be like this, right? And it will try to continue up to this portion, right? Like this. Okay. So before that, what will happen? Let me draw with another thing. So suppose if I want to draw the registered voltage here, so my registered voltage will be somewhat like this. So what will happen to the inductor there? So before that, the inductor value should be positive, right? So if I want to draw the inductor voltage, so my inductor voltage will be positive up to this part, right? And then it will be negative, right? Like this. Okay. So now if the inductor current is not zero here, so the inductor will, in the previous case it was trying to force this diode D1 to turn on, remain turned on, right? And that's why we had a negative output, right? But here when the voltage becomes zero, what will happen? The polarities will be negative here, positive here, right? So whenever you have a positive polarities here, then it will turn this diode on, right? And the inductor current, it will have a path, unlike the previous case when the diode D1 was the only way for the inductor current to flow in their current, right? So in that way, if the inductor L is pushing this diode to turn on, then how this circuit will look like during the negative half. So from the positive half, for the positive half, how the circuit will look like? The circuit will look like this. This diode will be short circuited, and once it is short circuited, what will happen? The polarities will be like this. So positive terminal will be here, negative terminal here will be here. So this diode, it will be in the reverse bias, right? So it will be turned off. So in that case, when it is turned off, then it will work like a open circuit, right? And then you will have a resistive load and the inductive load that you find previously, like, right, same circuit, and this is my output V0. We'll have the same circuit, right? But and the current, it will flow like this, right? And then we'll have this part. Make sense? But for the negative half cycle, what will happen? For the negative half cycle, so the circuit will look like this. So this terminal will be negative, this terminal will be positive. So this will make this diode turned on. So this is positive, this should be negative. And as you can see, if this is turned on and this is short circuited, so the entire input voltage, it will appear across the diode D1, right? Because if you do the KVL, you will find that the diode voltage will be same as the input voltage, right? Right? So then if I want to draw the waveform, so what will be my D1? So D1 would be, if it is my VD1, so VD1, it will be 0 because the diode was conducting, right? But as soon as it goes to the negative half cycle, the negative total cycle, it will appear across the D1, right? And however D2 or the freewheeling diode, so the first one, when D1 was on, so this thing is shorted, so the voltage across the diode, it is reverse biased, right? So the entire input voltage, it will appear across the diode, and here it will be conducting, right? D2 is on, and here this should be your VD2, right? Now what is happening to the then current? So as we can see, up to this point the current will be positive, but here when the voltage goes to 0, then what will happen to the current? What will happen to the current? The current will flow through this path, right? Rather going into the total circuit, right? So the discharging rate of the current, it will be dependent on the time constant L over R, right? Right? Because it's a simple RL circuit now without any excitation, right? So the diode will, what the inductor will try to do? It will try to discharge the current as soon as possible based on the time constant of the circuit, right? So now what will happen? So instead of having this part, now what we'll have here is that here we'll have the current, this discharging part, it will be dependent on the RL value. So if the RL value is high, you will find that it can go anywhere depending on the value of the RL value, right? Right? You understand what I am talking about? So now if you see that after a certain period of time the current will be in a steady state, and you can find the input current or the current IL, it will be like this. Any question? Any question? Is there very difficult to understand what I am trying to say? Why it is difficult? Because we have two circuits, right? One was when the diode D1 was on. So when the diode D1 was on, the voltage across the inductor, whether it was positive or negative, positive for a certain period and then it became negative, right? But when this diode, this D2 starts working, then what will happen? The voltage across the inductor or the total branch, it would be 0, right? So V0 would be 0, right? So if I draw the V0 now, what will happen to the V0? For the positive half, the V0 will be same as that of input voltage, right? But for the negative half, it would be 0, right? Like what we had for the resistive load, right? So in that case, we can keep the same output voltage as we had for the R load only, but here we can also control the charging and discharging current of the inductor. Any question regarding this? So now here, as you can see now, so I just here there is another diode section that I didn't connect before. So if I connect this section now, and if I keep the value as it is 100 in the previous case, now let me draw that circuit. So what will happen to the output? So now if I So as you can see, the restored voltage after a certain period of time it drops down to 0. Why it drops down to 0? Because the current becomes 0. The current suddenly discharges. That's why it becomes 0. So when you have a high value of R, what will happen? That time constant will be very low, right? So it will immediately discharge, right? So that will be very evident from this waveform. So here if you see, let me configure this one. So suppose this is my 4. So this current, let me put that 5. Okay, still this is very high. So can you see here? So this current is discharging current that is going through your diode 2, and this portion is actually making this portion of the inductor current. So now if I want to see the current of the diode D1, so the diode D1 is this portion. This is my full current and this is the dropping portion. So if you combine with this and this one, so this is my D1 and this is my D2. If you combine them together, that gives you the inductor current. Okay. So now if I increase the time constant, how we can increase the time constant? Decreasing the resistance. So now if I decrease the resistance, what will happen? Let me simulate that for 1 second. So now okay, so now just give me 2 minutes and I will let you go. So for here, as you can see, this is my diode current 1 and this is my diode current 2, and if I zoom it here, you will find that this portion is basically the charging portion of the inductor current, and this portion is the dropping portion of the inductor current, right? And this portion is mainly dependent on the value of R and L, right? If you make the tau higher, so it will be a straight line rather than it is going in a slope, right? So if you put a R value that is very low, like a 0.1, you will see that the current becomes a straight line. So if you put this value 0.1, 0.1, and if you draw the circuit, so you will find that this remaining portion, just I will draw that little bit and then I will let you go. So suppose this is 80, still it is not there because you have reduced the resistance by 10 amounts, so the current gets even bigger, right? But as you can see here, this thing is almost flat, right? So by increasing the time constant, you can make the discharging current stable, right? So if you have a, okay, so one thing, if you're in the exam, if I say, suppose you have a inductive load that is purely inductive load, meaning there is very small resistance in the circuit. So what will happen to the inductor current? What will happen to the inductor current? Suppose you have a rectified circuit that is connected to the inductor only, meaning that your L by R ratio is what? Tends to infinity. Then what will happen to your inductor current? What will happen to your inductor current? What will happen to your inductor current? What? It will be constant. It will be constant in the steady state. Okay, so as you can see, it is still rising, but after some times it will be in the steady state portion. So you will find that it will increase like this, and after some time it will be in a sinusoidal, but it will be in a steady state portion. So let me do that for 2 seconds. So as you can see, it will try to reach to its steady state value after 2 seconds, but it will be pretty much constant after a certain period of time. So inductor current will not vary after that, or you will have very small ripple in the inductor current. Okay, so the key findings of this circuit is that you can have your desired response depending on the value of choosing the proper value of L and R. And how can we increase the output voltage? By introducing a freewheeling diode at the output. Okay, so if you don't have any question, you are good to go for today.